Welcome back to the series of lectures on control systems. Today we are going to discuss about time domain analysis. In this time domain analysis, let us consider a transfer function C of s by R of s is equal to some s plus 4 by s plus 3. Now here this s plus 4 is known as numerator and s plus 3 is denominator. Numerator roots represents the zeros, denominator roots represents the poles. For example, if I solve the numerator, let us say s plus 4 is equal to 0. So from this s is equal to minus 4. This minus 4 becomes a 0. Similarly, look at the denominator. Denominator is s plus 3 is equal to 0. And from this s is equal to minus 3 is one root. So this one root is known as pole. From this, the conclusion is, if I find the roots of the numerator, it is going to give you the zeros of that transfer function. Similarly, if you solve the roots of the denominator, it is going to give you the poles of the given transfer function. Now let us take the another example. The transfer function is C of s by R of s is equal to s plus 3 into s plus 4 by s square plus 3s plus 2. Now if I see the zeros, you will get s is equal to minus 3 and minus 4. So there are two zeros for the given transfer function. Similarly, if you look at the poles, for the poles if you solve, what is the denominator? S square plus 3s plus 2 is equal to 0. Now this can be written as s plus 1 into s plus 2 is equal to 0. So from this s is equal to minus 1 and minus 2. These two are the poles. So for this transfer function, we have two zeros and two poles. Now let us see the another transfer function, which is nothing but the third one. The transfer function is equal to C of s by R of s is equal to 1 by s square plus 9. Now if you look at this transfer function, it does not have any zeros, and let us see the poles. To get the poles, s square plus 9 is equal to 0. From this, s is equal to plus or minus j into 3. Here j represents the imaginary term. So now here there are two poles, one is plus j3 and second one is minus j3. Now the next one is how to represent these poles and zeros on S plane. Representation of poles and zeros in S plane. Now if you see the S plane is nothing but sigma plus or minus j omega. What is the meaning? This sigma represents the real axis and j omega represents the imaginary axis, and this is anyhow origin. Now here this is known as right hand side of S plane. So this part is RH side and this part is left hand side. Now for example, what is the example? The first example is transfer function, that is C of S by R of S is equal to, we have S plus 4 by S plus 3. Now as I told you, if I solve for S plus 4 is equal to 0, that is S is equal to minus 4, it is going to give you a 0. And similarly the denominator S plus 3 is equal to 0, and if I solve this I will get S is equal to minus 3, and which is going to give a pole. Now if I want to represent this poles and 0 on S plane, this is real axis, this is anyhow negative real axis, and this is positive imaginary axis, and this is negative imaginary axis. Now all the zeros will be represented with a small circle. On S plane, if you want to represent a 0, it will be represented with a small circle. Now that 0 for this transfer function is at S is equal to minus 4. See, this is origin and this is negative real axis, minus 1, minus 2, minus 3, minus 4. And how to place this 0? 0 is at minus 4. So now I am representing with a small circle to represent or to place a 0 on S plane. Similarly, to represent pole, this pole will be represented with a simple cross symbol. Now at S is equal to minus 3 we have a pole for this transfer function. So at S is equal to minus 3 will be represented with a simple cross. This is how a pole 0 will be represented on the given S plane. Now let us take the another example. Transfer function is second example. Previously we have taken S plus 3 into S plus 4 by S square plus 3S plus 2. What are the zeros? Zeros are S is equal to minus 3 and minus 4. What are the poles? Poles are minus 1, minus 2. Now first let us draw the S plane. This is positive sigma, negative sigma, positive imaginary axis, and this is a negative imaginary axis. Anyhow it is origin. This is minus 1, minus 2, minus 3, minus 4, minus 5 and so on. Now let us start with poles. Poles are at minus 1 and minus 2. So this is a pole, will be represented with a cross symbol, and another one is at minus 2. And how to represent these zeros? Where are the zeros? At minus 3 and minus 4, and those will be represented with a small circle at minus 3 and at minus 4. So this is how we are going to represent the poles and zeros on the given S plane. Let us quickly see the another example. Say the transfer function C of S by R of S is equal to another one is, let us say, S square plus 9. This is what the third example we have considered previously. Now there are no zeros for this transfer function. We have only poles, and those poles are at S is equal to plus or minus J3. Now how to represent those? in S plane, this is 0, and this is positive imaginary axis, this is negative imaginary axis, positive real axis and negative real axis. And let us say this is at J1, J2, J3, or you can represent 1, 2, 3 since it is imaginary axis associated with J, and this is minus J, minus 2J, minus 3J and so on. Now here the poles are at plus J3, poles means cross symbol, and another one is at minus 3J, right. See, denominator we have s square plus 9. So since it is a quadratic equation, we have two roots, and those two roots are, one is plus J3, second one is minus J3, right. Let us see the another example of transfer function C of s by R of s is equal to numerator is s minus 6, denominator is let us say s plus 1, s plus 3 and s minus 4, s minus 4. Now what are the zeros? Quickly tell me. Zeros or minus 6, that is s minus 6 is equal to 0. What is that you will get? S is equal to 6 plus 6 here. So only 1 0. How many poles? So there are 3 poles. Those are minus 1, minus 3 and plus 4. And how do you represent these poles and zeros on the S plane? This is positive real axis, negative real axis, and this is positive imaginary axis, and this is negative imaginary axis. This is origin, positive side 1, 2, 3, 4, 5, 6, and here minus 1, minus 2, minus 3, minus 4. First let us place the zeros. Where are zeros? At s is equal to 6. See, this is right hand side, since it is a positive 0, positive 0. Where are the poles? One is at minus 1, that will be represented with a cross symbol. Where is another pole? At minus 3, and the another pole is a positive pole, that is at 4. See, we have placed all zeros. There is only one 0, that is at 6, and there are 3 poles, so at minus 1, minus 3 and 4. So this is how we are going to represent the poles and zeros on the given S plane. Now let us see the one more example of having complex conjugate poles. To get complex conjugate poles, let me consider the transfer function C of s by R of s is equal to s plus 3 by s square plus s plus 1. So if this is the given transfer function, let us see how we are going to find the poles and zeros. After finding the poles and zeros, then how to represent those poles and zeros on the given S plane. Now what are the zeros? Zeros are at s is equal to minus 3, since s plus 3 is equal to 0, and if I find the root, s is equal to minus 3. And how to do the denominator, how to get the roots of the denominator? S square plus s plus 1 is equal to 0. Since it is a quadratic equation, how you are going to find the roots? s1 comma s2 is equal to minus b plus or minus square root of b square minus 4ac by 2a. And if you substitute s1 s2 to get two roots s1 and s2, you will get s1 is equal to, what is the value? Minus 0.5 plus j 0.866, and the another root is s2, that is minus 0.5 minus j 0.866. So now these two are poles and this is at 0. Now draw the pole 0 plane. This is pole 0 plane or S plane, I can say, since we have not represented so far poles and zeros. This is a positive real axis and this is a negative real axis, and this is a positive imaginary axis and this is a negative imaginary axis. And anyhow, 1 0 is at -3, so let us say this is -1, -2, -3, and 0 is at -3, so it will be represented with a small circle. And now poles. So poles are at -0.5 plus j 0.866 plus j plus positive imaginary axis. Let us say this is j 0.866 and another one is minus j 0.866. Now it is combination of both real part and imaginary part. Where is the real part? It is at -5, -0.5, sorry, -0.5, and if I extend this and if I extend this, so there is a common point, so this is going to give you your -0.5 plus j 0.866. So this is your pole. This is your pole. And similarly, if I extend the negative side, and somewhere here you are going to have the another pole, that is -0.5 minus j 0.866. So far quickly, if you see, we have taken the poles on negative real axis, poles on positive real axis, and we have seen a pure imaginary values and complex conjugate. So these are the various types of poles and zeros we do have, and we have seen the representation of those poles and zeros on the given S plane. Next, let us see the stability conditions, very important. Stability conditions. When come to stability conditions, as we discussed it so far, if you solve the numerator you will get zeros, and if you solve the denominator of the given transfer function you are going to have the poles. Now when you are going to discuss about the stability, zeros never affect the system stability, so we don't have any problem with zeros. Zeros are never going to affect the system stability. Now only the problem is with poles. Depends upon the type of poles, the stability conditions may vary. Now we will see one by one. In the first case, case 1, on the given S plane, if I find the poles only on negative real axis, that is this side, left hand side, -1, -2, -3. For the given transfer function, let us say all the poles are lying on the left hand side of the S plane, left hand side of the S plane. Now we can say the system is stable. I repeat, for the given transfer function, if all the poles are lie on the left hand side of the S plane, then we can say that system is stable. Now in this case the poles are said to be on placed on negative real axis. This is case 1. Next let us go to the case 2. If poles are negative and complex conjugate. In the previous case poles are only negative. Now in this case we see if poles are negative and complex conjugate. For example, the poles are like S1 comma S2 is equal to minus 0.5 plus or minus j 0.866. In this case we have already seen the representation of these poles on the S plane, plus sigma minus sigma plus j omega minus j omega. Now how we are going to have these poles on S plane? This is minus 0.5, this is plus j 0.866, this is minus j 0.866. Now if I extend this, now we can say this is one pole and this is another pole. Now in this case we can say the system is stable. So in this case also we can say the system is stable. Next go to the third case. Case 3. In case 3, if I assume all the poles are on imaginary axis, if all the poles are on imaginary axis. So for that, what is the example previously we discussed? Say you have equation like s square plus 9 is equal to 0. In this case we can say s is equal to plus or minus j 3. That means on the S plane where is plus j3, since it is a positive imaginary axis, so you have plus j3 and this is minus j3. Now if I represent poles, this is one pole and this is on another pole. Now see, poles are lying on the imaginary axis. If poles are lying on the imaginary axis, then we can say the system is marginally stable. The system is marginally stable. Next, the another case, case 4. If the poles are on imaginary axis and they are repeated. For example, let me take the previous example. What is it? S square plus 9 is equal to 0. Repeated means s square plus 9 whole square. Now how to get the poles? This I can say s square plus 9 is equal to 0, and one more is also s square plus 9 is equal to 0. See, s square plus 9 whole square, so you will get s power 4. So obviously you are going to have 4 roots. Those 4 roots are plus j3 minus j3, again plus j3 minus j3. Now how we are going to represent on the S plane? this is a positive imaginary axis, negative imaginary axis, positive real axis, this is negative real axis. Now if I assume this is plus J3 and this is minus J3, what is happening here? Poles are repeated. So at plus J3 we have two poles, at minus J3 we have two poles. So this is how we are going to represent if there are multiple poles. Now the conclusion is, if poles are on imaginary axis and repeated, we can say the system is unstable. The system is unstable. Now let us go to the next case. In this case, if we assume if at least one pole, if it is on the right hand side of S plane, that means on the given S plane, this is positive sigma and negative sigma, positive imaginary axis and negative imaginary axis, at least one pole, let us say it is at 3. If there is at least one pole on RH side of the S plane for the given transfer function, if at least one pole on the right hand side of the S plane, then we can say this is RH side. Then we can say, without looking at the other parameters, the system is unstable. Next, the overall representation, if I see for a given S plane, this is a positive sigma and this is negative sigma, positive imaginary axis and this is a negative imaginary axis. This side, this is RH side and this is the left hand side. This side, right hand side, is system is unstable. Left hand side is stable. And what about only on imaginary axis? Marginally stable. So this is how we are going to define the given system stability. The conclusion is, for the given transfer function, after finding the zeros and poles, if you place those poles and zeros on the S plane, if you find all the zeros, anyhow zeros will never affect the system stability. We are concentrating only on the placing of poles or placement of poles. If at least one pole is on the right hand side of the S plane, then we can say the system is unstable without looking at the remaining poles. And the second one is, if I find all the poles are lying on the left hand side of the S plane, I can say the system is stable. The next one is, if the poles are negative and complex conjugate, then also we can say the system is stable. Now if the poles are purely imaginary, if the poles are purely imaginary or the poles are lying on the imaginary axis, then we can say the system is marginally stable. And the next is, if the poles are imaginary and repeated, repeated on the j omega axis. If poles are repeated on the j omega axis, then we can say the system is unstable. So this is one part in the time domain analysis. Let us go for the next time response. This is another very important topic in time domain analysis. Here we will see the time response of a first order system. Similarly, time response of a second order system. In CO1 or in the first unit, the outcome is transfer function, that is C of s by R of s is equal to something, some s plus 1 into s plus 3 by something s plus 4 into s plus 7, let us say. Now here in this time response, we are going to find the response of the system. To find the response, we need to have R of s. R of s is your input. After applying the input to this transfer function, what it becomes? C of s is equal to s plus 1 into s plus 3 by s plus 4 into s plus 7 into R of s. And after substituting R of s here, we are going to have C of s equation, and after that normal procedure, applying partial fractions, separating the terms, and then applying the inverse Laplace transform to get the C of t. So this is what we need to find out in time domain analysis or in case of time response. Response means with respect to time, we are going to find the output. That output here we will call it as C of t. C of t. Now before I do first order system response, second order system response, let us see what are the various standard test signals available. Standard test signals. Generally, we do discuss there are 4 standard test signals. In that, the first one is impulse, second one is a step signal, third one is ramp signal, and the last one is parabolic signal. Now let us see complete information about each signal, like what is the mathematical representation of the each signal and what is the Laplace transform of that either impulse signal, step signal, ramp signal or parabolic signal. Now first let us see the impulse signal. It is represented with del of t, and this del of t is equal to 1 for t is equal to 0, and which is equal to 0 for t not equal to 0. And how you are going to represent mathematically is this one, and graphically as t is changing from 0 to infinity, and here at t is equal to 0 it is 1, that is this signal. This is del of t, and del of t is equal to 1, or I can say some k. K is anyhow a constant value. This k may be 1, 10, 20, 30, 34, whatever it is, right? Now if at particular instant, if let us say k is equal to 1, in k is equal to 1, del of t becomes 1. In this case, this signal is known as unit impulse signal. If the magnitude of the given impulse signal is 1, then we can say it is a unit impulse signal. And what is the Laplace transform? Del of s is equal to 1. This is the Laplace transform of a impulse signal. Del of s is equal to 1. And this is first one. And similarly, I will write the equations for step signal. Second is step signal. So hope we know the basics of the step signal. U of t is equal to 1 at t is greater than or equal to 0. Let me write quickly. U of t is equal to some constant k for t greater than or equal to 0, and is equal to 0 for t less than 0. And this, if I represent, this is how the step signal will be. This is t, this is u of t. As usual, if k is 1, then u of t becomes 1. So in this case, it is said to be unit step signal, right? And if I find the Laplace transform, then u of s becomes, it is 1 by s. If it is k, it is k by s. So this is fundamentals. And third is ramp signal. Here I am writing directly the Laplace transform of ramp signal, that is r of s is equal to 1 by s square. Since we know from the basics what is the value of r of t? R of t is equal to some constant k into t for t greater than or equal to 0, and it is equal to 0 for t less than 0. That if you represent mathematically, that is the equation, and from graphical representation it is 0, and see it is t, so it increases linearly with respect to time. Let us say this magnitude is some k, and this is your r of t, and Laplace transform is r of s is equal to 1 by s square. Okay. Next, and in the similar way for parabolic signal, let us say that parabolic signal is some g of t. G of t is equal to some k into t square by 2 for t greater than or equal to 0, and is equal to 0 for t less than 0. And the graphical representation is like this. This is, let us say, your g of t, and this is t, and let us say this magnitude is some k. And what is the Laplace transform? G of s becomes 1 by s cube. This is Laplace transform. This is also Laplace transform of ramp signal. So these are the 4 test signals we have. Out of these 4, we can say step signal is the best signal for testing. We will see in next couple of classes why we are going to consider this step signal for testing the given system. Okay. Now let us see the response of the first order system with the impulse signal, step signal, ramp signal and parabolic signal. Now for that, what is the first order system? Quickly, if you see from the previous classes, first order means it is an RC series circuit. You have input Vi of S, output we do consider at capacitor, that is C, and this is R. And if I find the V naught of S by Vi of S becomes 1 by RCS plus 1. This we have seen in the previous classes. From this, we know the time constant of RC series circuit is tau is equal to RC seconds. Now if I substitute and V naught of S by Vi of S becomes 1 by tau S plus 1. Now what is that I will do is, by rearranging V naught of S by Vi of S is equal to 1 by tau by S plus 1 by tau. Now normally the output we do consider as C of S, the input is R of S, and this becomes 1 by tau by S plus 1 by tau. This is the first order system transfer function. Now if I represent the same in block diagram representation, I will have positive plus, and this is your 1 by ST S tau, C of S is the output, R of S is the input, and if I take the, since it is unity feedback, and finally you will get the value becomes either C of S by R of S is equal to 1 by S tau plus 1 or 1 by tau by S plus 1 by tau. So here just I represented in block diagram representation. Now let us see the impulse response of the first order system. What is first order system transfer function? C of S by R of S is equal to 1 by tau by S plus 1 by tau. So impulse response, that means the input is impulse signal. Now directly I am writing Laplace transform of impulse signal is 1. Previously we have seen, since here I have considered the impulse signal magnitude is 1. Now this C of S becomes 1 by tau by S plus 1 by tau into R of S, that is 1. Now if I apply inverse Laplace transform, because here the term is like 1 by S plus A. At this case we can apply directly the inverse Laplace transform. Then C of S becomes C of t, since the inverse Laplace transform is going to convert the given S domain into time domain, right? So as simple as Laplace transform will convert time domain into frequency domain, that is S domain. Inverse Laplace transform is going to convert S domain into t domain. Now here we are applying inverse Laplace transform. This C of s becomes C of t, and anyhow 1 by tau is a constant, and L inverse of 1 by s plus 1 by tau, which is nothing but 1 by tau into e power minus t by tau. What is the response now here? C of t is equal to 1 by tau into e power minus t by tau. So this is the system response. Now if I plot the response, let us say this is your C of t and this is time t, it is 0. Now see, by substituting various values of t, let us plot the response. At t is equal to 0, if I substitute here at t is equal to 0, then e power 0 is 1, so you will have 1 by tau. So at t is equal to 0, the magnitude is 1 by tau, and as time increases, say for example in the ideal case at t is equal to infinity, if I substitute t is equal to infinity, e power minus infinity is 1 by e power infinity, that is 1 by infinity, which is equal to 0. That means as time increases, the response decreases in this fashion. So at this point your response reaches to 0, C of t becomes 0. So when C of t becomes 0, we say theoretically at time t is equal to infinity. But if you do the same practically, we do find at t is equal to 5 tau, we do find the system response almost reaches to 0. We can say the C of t equal to 0. So this is very important question. I repeat, theoretically we do substitute t is equal to infinity to get the value of C of t is equal to 0, but while doing practically it is not possible to substitute t is equal to infinity. So we found that at t is equal to 5 tau almost the system response reaches to 0, and this we do consider the practical case, right? And let me give you one simple question on this. After how many time constants the system reaches to steady state? I repeat, after how many time constants the system reaches to steady state? Okay, now the answer is after 5 time constants, that is t is equal to 5 tau, right? So we have one experiment also in our lab. There you can clearly observe how this C of t becomes 0 at t is equal to 5 tau, right? Now this is the impulse response of the first order system, right? Now what is the observation here? Look at the C of t value. This C of t value is having alone e power minus something, right? If any response it has alone e power minus t by tau or e power minus something, you remember the system response will be exponentially decreasing value. See, this is exponentially decreasing. At t is equal to 0, the value is 1 by tau, and as time increases the system response reaches to 0. So this is known as exponentially decreasing function. Exponentially decreasing function. Okay. Now let us see the same for unit or step response of the first order system. step response. So what is first order system? C of s by R of s is equal to 1 by tau by s plus 1 by tau. What is input? Nothing but step response, that is R of s is 1 by s, since u of s is 1 by s. Here R of s is equal to u of s. Now if I apply the step signal to this first order system, what is it I will get? 1 by tau by s plus 1 by tau into R of s. That R of s is anyhow 1 by s. Now see, in this case it is not possible to write inverse Laplace transform directly because it is not in the standard form. Now first let us bring this C of s into standard form to apply inverse Laplace transform. For that, first apply the, or first try to get the partial fractions. So how to get the partial fractions? This 1 by tau by s into s plus 1 by tau will be written as a by s. This is from the 7th or 8th mathematics. A by s plus b by s plus 1 by tau. And if you solve this, finally you are going to get, I am writing directly C of s value. C of s you will get 1 by s minus 1 by s plus 1 by tau, because you know how to write the partial fractions. So finally you are going to have 1 by s minus 1 by s plus 1 by tau. Now I can say this is in the at this stage it is possible to write the partial fractions, that is inverse Laplace transform. So after applying inverse Laplace transform, what is that I will get? C of t is equal to L inverse of 1 by s, that is 1, minus L inverse of 1 by s plus a. It is in the form of 1 by s plus a. It becomes e power minus t by tau. So this is very important equation. Step response, as I told you, we do consider the step signal is the best signal for testing. Now this is how the response will be. C of t is equal to 1 minus e power minus t by tau. And if you plot the response, this is t and this is C of t, this is 0. Here also we do draw the response curve by taking different values of t. At time t is equal to 0, so e power minus 0 is 1, so 1 minus 1 becomes 0. So at time t is equal to 0, the response, that is C of t, is 0. Now as time increases, let us say at time t is equal to infinity. At time t is equal to infinity, so e power minus infinity, that is 0. When e power minus infinity is 0, 1 minus 0 becomes 1, so C of t is 1, so maximum value is 1. Now the plot will be like this. Now previously I told, while doing practically, we can say the system reaches to C of t equal to 1 at 5 time constant, t is equal to 5 tau, right? Now if you observe this response from 0 to 5 tau, what is happening? The response is changing with respect to time. The response is changing with respect to time. If the response is changing with respect to time, then we can say that is transient response, TR, transient response, right? Now from 5 tau to t, even if I change the value of t, the system magnitude is constant, which is equal to 1. This is known as steady state response, right? Now you can easily find from the expression the term which is related or associated with time is going to give you your transient response. This is your transient response. And what about this? This is not associated with time, so it gives you your steady state response. What is the conclusion? As time increasing, the transient response will vanishes. See, from 5 tau to t, there is no change in the magnitude of the response, which is equal to 1. That means at the output you are going to see only C of t is equal to 1. Okay. Now the one more point is, if you have the term like 1 minus e power minus something, 1 minus e power minus something, let us say here you have 1 minus e power minus t by tau. Now if you have term like that, then your response is exponentially increasing. Previously, you see, you have the term alone e power minus something. If you have term alone e power minus something, okay, whatever the magnitude is, the magnitude may be 2 into e power minus t by tau, 3 into e power minus t, whatever it is, right? But the term is alone e power minus t by tau. In that case, the conclusion is the response is exponentially decreasing. And the next case is, if you have term like this 1 minus e power minus something, then the response will be exponentially increasing. So this is how the step response of a first order system will be. Similarly, you can see the directly, let me write the ramp signal response. See, in all these cases I am considering unit, that is magnitude is 1. Here also it is unit ramp signal. Okay. Now, so R of s is 1 by s square, C of s by R of s is equal to 1 by tau by s plus 1 by tau. Now C of s, you will get 1 by tau by s plus 1 by tau into R of s, that is 1 by s square. Now this also you may write a by s plus b by s square plus c by s plus 1 by tau. After writing and after finding the partial fractions, so you will get your C of s becomes, I am writing directly 1 by s square minus tau by s plus tau by s plus 1 by tau, and after applying the inverse Laplace transform, you will get C of t is equal to L inverse of 1 by s square, that is t, minus tau plus tau into e power minus t by tau will be your response. this is your ramp signal R of t, okay, and if I find the values C of t at different values of t at t is equal to 0, so what is it you will get? It is something like exponentially increasing like this. This is your C of t. Now here what is the conclusion? Tau is anyhow constant and two more terms are associated with time. Finally you are going to remain with tau value, that is your C of t, okay. Next, unit parabolic signal, last signal. And parabolic signal, I have taken g of s, okay, and it is 1 by s cube, and again C of s by R of s is your 1 by tau by s plus 1 by tau. After applying partial fractions and all, you are going to get the C of s value, and then C of s is 1 by tau by s plus 1 by tau into R of s, that is 1 by s cube. And how you are going to write the partial fractions? 1 by tau into s cube into s plus 1 by tau becomes a by s plus b by s square plus c by s cube plus d by s plus 1 by tau. Try to solve this and find out the value of C of s, and then apply the inverse Laplace transform, and then find out the C of t response and try to plot the response curve C of t, right. So this is your homework. Next, we will continue the second order system in the next class.